I've redrafted this talk. The original intention was to talk about the difficulties of designing systems. And the reason why I redrafted the talk is because I've been thinking about some of the problems I'm going to discuss with you. I think the actual occurrence of these problems are actually well known to you. So you'll probably all know about things like the Savannah Express. So the engineer says to the captain, I'm not really sure how the electronic system works on this engine. Yeah, he actually says that. The captain reports to the pilot, I think everything's okay. And then the engineer who's told by the company that supplies the system that when the sensor trips out, it won't trip out the engine, but it does. And then the boat goes headlong, under no control of propulsive power, into a large piece of metalwork in the harbour. So we don't expect our systems to operate like that now, do we? We don't expect to have surprises. So the people on the Viking Sky didn't expect that when the boat was heaving, sorry, I don't mean to make you sick there, heaving backwards and forwards, that in some sense the sensor detecting the actual oil level would fail to detect that there was oil there, think, oh, the engines will be damaged, I'll switch the engines off, trip the engines out, so you have no propulsive power, so you have no control over the ship. And I think this is something we have to realize. Someone has said this earlier on in the day, automation is not clever. It is not smart, it is not context sensitive. We know this, and it's writ large in many, many accidents we see. It's not that I'm a technology naysayer, I'm just saying, if you're going to introduce technology, you're going to have to up your game. You're going to have to improve on what you're currently doing. And as we've seen with the 737 MAX 8 example, if we didn't have an onboard recording system, would we really know now that the pilots were not at fault? What would Boeing be saying? So if I'd said to you, before these accidents and before the recent discussion happened, that's not possible, Boeing wouldn't introduce an unsafe system, you would be saying to me, oh, there's no possibility of that ever happening. Okay? But when you look at these narratives and stories, what you often do as you unpack it is you find many other factors at work. So for example, in the Savannah Express case, the engineer didn't have sufficient training to understand the systems he was controlling. So could you really blame him? Well, you suppose you could say he should have refused to take the job because professionally he should have been competent to do what he was doing, but he didn't understand the systems. But then again, neither did the company that supplied the systems to the actual ship. So there's a whole chain of things that usually go on in accident sequences that reveal to us the complexity of working in the real world. And I think that's something that Cormac picked up earlier in his talk. Okay? Before I go on, I should just mention one thing. Right. Now, here we, oh, is it? Ah, there we go. So I should mention this at the beginning. This work has been generously supported by BAE Systems Maritime, and attendance at the conference is supported, but the views that I'm expressing are my own. So I take full responsibility. Now, having revealed to you the idea there's a problem, so I'm not going to even attempt to get through all the slides I have today, but I might skip through a few just to get to some critical points that I want to make. So, what this is, you see in front, you don't, it's only there for a figurative purpose. It's part of a safety case. There was an analysis done by NASA of safety cases. And what they found is that in the vast majority of safety cases that people produce for systems, so they're outlining the design of the system and the safe operation of the system, most of the arguments that are made are fallacious, false, wrong, inaccurate, misleading. People make claims about things which are not true or can't be substantiated. Okay? So when people design systems, we don't design them well in terms of truth. That's just the way it is. The thing that actually comes forward from this is that quite often, and I've noticed this today, and this is not picking on any individual person, when people make statements, quite often they make statements which have a consequence which we don't unpack, and therefore we don't reveal, in fact, it's very difficult to do them. So for example, a lot of people have mentioned things like AI, artificial intelligence, and learning systems. Now, we build systems that do things, but they always do the same thing under the same context, in the same conditions, and so on. They don't change. How do you certificate artificial intelligence or a learning system? Because it changes from the state it was in before, particularly if you add evidence to it that changes the way it looks at the world, it then changes certification. In other words, the models that we have for verifying, proving the safety cases that we want to do for these new systems, we don't have. And in fact, one of the things I would say to you that I've kind of realized of late, in the maritime domain, and apologies, I come from the aviation domain, so that's my background, it's just history. In the maritime domain, we're a lot further down the curve, going back the way, in the sense that we may actually be adopting practices from other industries who have a more sophisticated view of the world about how we should actually verify and validate systems, because we don't have them in the maritime world. That's particularly true of electronic systems. And even in the aviation world, as you've seen with recent incidents, sometimes it can be very difficult to produce a good safety case, even if we have good guidance and good regulation. It's very, very difficult to do. So that's the point about that. It's very difficult to construct a safety case, and in the vast majority of times, the important thing to stress, it's not about intelligence, it's not about training, because what you often find, people have looked at this, they've tried to train people not to use false arguments. You can improve, but you can never be perfect. Just take that as a convincing point of view. You could think about all the things you've heard today, and people will have made false statements which are not testable or provable. Okay? And they've asserted that they are the God-given truth. Okay, so the next thing is that most people learn best by active participation. This runs counter to what we know about automation. Automation is to take the job away from you and get something else to do it. We used to have a joke in the aviation world that in the future cockpit, you will have a person, a dog, and a computer, right? The person is there to feed the dog. The dog is there to bite the person should they try and touch the equipment, right? And the person is also there to take the blame when it all goes wrong. There's a truth behind this. We quite often talk about the domination of human error in the consequence of systems, but why did the person make that mistake? Maybe it was prompted by the system they were using that wasn't telling them the right information in the right form that they could understand, therefore they could stop the accident happening. Quite often, and I've had this question asked, we talk about accident investigation and we come to the point where we find the human being and we stop. And it's interesting because the comment that was made with respect to the 737 crash is we already know that perhaps the human beings involved in trying to control the plane were unable to control it because the system said no. The computer effectively said no. And they weren't aware they could switch the computer off because they hadn't been trained, because it wasn't necessary, because it was good to make the transition to a new aircraft by doing less training. You see there's a common theme coming up. There's kind of 6 pillars of wisdom in design. You want to look at the human factors engineering, the design of the system and the use of the system. You want to look at human error. You want to look at training. You want to look at the documentation. And you want to look at the safety culture in which that is operated. In other words, you wouldn't fly on an operator that would try and get to the terminal building as fast as they could from landing, would you? Because you know where that's going to end up. So all these things wrap around in terms of safety. Active processing of information makes recall more effective and decision-making better. That's exactly what automation prevents. It doesn't involve you, it doesn't engage you. So why are we surprised that we're still left with a lot of human error? The tricky thing is, in aviation, we talk about automation surprises a lot, which is where you press a button and what you think should happen doesn't happen. The classic one being the Mulhouse-Absheim crash with the Airbus initially. They're flying the aircraft along the runway, and the only way they can get it that slow is to tell the aircraft they're landing. They then notice there's trees at the end of the runway and think, yeah, we better get out of here. They push the throttles forward, nothing happens because the plane is saying you're landing. You don't need extra engine power. I'm not giving you extra. Nothing's happening. So that's the first illustration of where the mental model the pilot has, which is I have control, and the system is different. The model that's built in the system is antagonistic. So I'm not against automation. It's just it's a lot trickier than you might imagine. The other thing as well is the whole model we have for learning and training is very poor. We don't understand how we deal with exceptions. And that's particularly true with automation. Learning is not just a simple curve. That's the important thing I was going to try and get across there. The next thing to consider is that there's the training to use the system without automation, so in manual mode. And we've kind of touched on this in a way indirectly. The system's quite complicated. Well, the Savannah Express, the guy didn't understand the system. So quite obviously you need additional training to know how to use the system when the automation's in place. But what happens when the automation fails and you go through the transition phase between the automation and the manual mode? There's a state which is different from both manual and both automation. So you now need 3 training programs. You need the training program for the automation, the training program for the manual, and the training program for in between. In other words, it's more complicated, not less complicated, particularly when the system is partialized, partially automated. Okay, it becomes really, really difficult. Now, the slides I'm presenting to you come as part of a training pack, which I'm doing for some of the people within my own organization. And for my sins, I'm now involved in marking other people's homework and reviewing whether what they're saying actually meets the burden of proof. So I'm quite interested in this, which is the standard V model of systems engineering. And one of the things I've noticed, if I can do this little bit in the middle, which is now in the dashed area, the link between the requirements, right? So she's thinking about the design intent, and then the actual verification and validation. That's where the gap exists. So what can happen is, if you look at systems, and there are examples there, Ariane 5, they put the Ariane 4 rocket program on the Ariane 5, not realizing the requirements didn't fit. The rocket blew up on takeoff, okay? So they fitted the wrong model to the wrong requirements. This is a medical system, the Therac 25. They didn't get the requirements right. The outcome was a lot of people died. And there are other systems that you can get in there. So aviation automation is another example where if you don't get the requirements right, you don't get the outcome you want. We know this is a consistent pattern with many systems that have technology in them. We don't get the requirements right. If you don't know what the system has to achieve, you can't then demonstrate and validate it. Do you remember I was saying there about a system which learns? So let's take a learning system and put it on the left-hand side and then think, how are you going to verify and validate it if it changes every time it learns new information? You're not going to be able to do it, are you? It's going to be very expensive. One of the things we quite often, I think, see within the maritime domain as well is the weakness of understanding the system engineering model. We tackle subsystems, so we introduce things like ECDIS, but we don't think about the way it puts other activities out of shape. So if you go above, it's the system integration piece. So if this guy's going to use ECDIS, what else is he going to do at the same time? Or this lady is going to use ECDIS, what's she going to do at the same time? What other activities? So accidents might not happen because of the system that's been introduced directly, because of the system and the activities it's involved in, but the activities it affects. So we heard that story of people looking down in the screen, not looking out the window, or looking out the window and not looking down at the screen. So do you understand the context of use of your system? And do you test it out in terms of a fully integrated system model? I would argue in many bridge systems you don't, because you keep the ship. You say, oh, we've got space over there. And I've heard this said, actually, at an arena conference. We've got a bit of space over here. We'll fit that bit of technology in over there. It doesn't matter that the guy over there is meant to use that over there and has to do this at the same time. That's very poor systems integration. Okay, how are we doing for time? Okay. So, I've not really made a dent on my talk, but I hope I've kind of convinced you there are some big questions to be asked. We cannot glibly apply this is the case. We have to substantiate and verify what we're saying and provide a convincing argument that isn't based on false premises. And I think what we've done is we haven't really done that. Now, I want to just end with one last little observation, which actually, again, doesn't relate to human factors, but it relates to some of the things that are keeping me awake at night. Currently, we quite often rely on what's called process-based certification of systems. We try and collect evidence that a system has been thought through in appropriate ways, validated and verified in appropriate ways, and document all that evidence together. Now, in a very significant case in UK law, Haddon Cave, what the actual Queen's Counsel found was they had documented everything and understood nothing. Process-based certification can do that. It can provide you with mountains of evidence about absolutely nothing. What we really need, and this was quite interesting listening to Cormac's talk, we need people to think about what they're doing, to understand the consequences of what they're saying, and properly try and envisage them as best they can. We need to look to the future and understand what the consequence will be. And quite often people say, it's a bit like in Star Wars, you know, where he says, these are not the droids you're looking for. This is automation. You don't need to know about this. You do. You really need to know what the box in the corner is doing, what it will do to what you're trying to do, and whether it will help you or hinder you. Okay? And on that note, I'll stop. Yeah?